Howdy there, Mr. Sutton here, bringing you this AB Calculus 3-4 lesson on graphing derivatives. In this one, we'll be drawing and recognizing the graph of a function's derivative based on the original graph. For our warm-up, we're going to start by graphing the derivative of a piecewise function that has all lines in it. So pause the video, take a sec, and in pencil, see if you can figure out what the derivative of this should look like. And here's a hint, you're graphing the slope of f at all these points. Now, as you're doing this, let's just go from left to right and observe what we see and what it should turn into for the derivative graph. Here we've got a constant slope. From here to here, this is a constant slope. So if your slope is constant, that means that your derivative is going to be a constant number, which means that the derivative itself is just going to be a flat horizontal line. And we also notice that we have a corner here. We're changing abruptly from one slope to another. So for your derivative, that means you're abruptly changing from one constant to another. So at a corner, then, we would expect you to be jumping from one constant to another. And since we know that you're not differentiable at corners, that jump should have open dots in both places. So let's go ahead and graph that piece of it. Right here we have a slope. We're going up 1 over 2, and we won't always be able to tell the exact slope, so we should savor this moment because it's not always the case. But we have a slope of 1/2 from here to -2, so here's 1/2 from here to -2. We'll do an open dot here because we are abruptly changing slope once we get there. After we get to -2 and until we get to +1, we have a slope of 0 up here. It is a constant slope of 0. So that means our slope down here, we're just going to put a horizontal line on 0 from -2 to 1. Now, the next thing we might observe before we move on to this last branch is that we have this hole in the original graph. And we know that at a hole, if the original function doesn't exist there, neither does the derivative. So a hole in the graph, a hole in the original, and the derivative are going to match with each other. So we'll put a hole down here at -1. And now this last piece, we're going down 2 and over 1. This is a constant slope of -2. So from here, we're going to jump down to -2 for another horizontal line. Let's tackle some slightly more advanced functions. So on these functions, unlike the last set, we have a whole bunch of curves. Which is to say we can't really pick out a constant slope in most of the spots on this graph. But we can still draw a few conclusions. In this graph, sometimes we are increasing, sometimes we are decreasing, and sometimes we are having a smooth turnaround. So if we're increasing on the original graph, like over here, we know that the derivative is going to have to be positive. If your numbers are going up, you've got a positive slope. At the same time, if your numbers are going down, if your graph is decreasing, then your derivative has to be a negative number. You have to have a negative slope if your original function's going down. And when you have a smooth turnaround, like right here where you're changing from a negative slope to a positive slope, you're going to have to go through a slope of 0 right here to do that. So with that in mind, let's see if we can tell what these graphs should look like. So on this first parabola, over here, we're decreasing at a pretty decent rate. So that means we're going to start off in negative land for our derivative. A lot of people have trouble graphing derivative graphs because they have trouble realizing that although all the x values up here correspond with the x values down here, it is the slope of this function up here which is giving us all the y values down here. So the y values of the original don't really make any difference. It's all about the slope. And here our slope is negative, so our y values down in derivative land are negative. Now, although we start negative, we're getting less and less negative, closer and closer to a slope of 0 as we go, to the point where at 1, we actually have a slope of 0. So we can graph the first half of this as a function that looks kind of like this. It doesn't have to be a line, but it's got to be going closer and closer and hitting the x-axis at that smooth turnaround, at that point where the slope is 0. Now after that point, we have a positive slope, and it's getting steeper and steeper and more positive. So after we hit the x-axis down here, we should just keep going. So pause the video and see if you can figure out what the graph of this downward slope, downward facing parabola should look like. All right, let's see if we have the same thing here. We start with a pretty positive slope that eventually gets down to 0 at x equals 1. So this is kind of like the first graph, only we start up here and we're getting less and less negative until we hit a slope of 0. After that, we're getting more and more negative for our slope, so this is going to keep going down here for our y values on the derivative. Now, one quick thing that's interesting to note before we move on, we don't know for sure that these are x squared and like a negative x squared kind of function, but they could be. If this was x squared, what's the derivative of x squared? Well, it's 2x, which is a line, right? The derivative of a parabola should look like a line. For these next few examples, we're going to take a look at some oddball features. On this first example here, we notice that we have a cusp. So if we think about what's happening to the slope here we are getting more and more and more negative, infinitely negative, and right here we're switching immediately to infinitely positive. So whenever you have infinite slopes involved, you're going to have an asymptote, a vertical asymptote, on the graph of your derivative. So on our derivative, we start off going infinitely negative, and then right away we're infinitely positive. So here's what that graph is going to look like. Infinitely negative as we head towards that asymptote, and then here's the infinitely positive part, which you'll notice the slope is less and less over time, eventually tapering off to close to horizontal. Over here, we have a vertical tangent. Now, the vertical tangent, remember, you're approaching the same infinity. So that's going to be another vertical asymptote because you've got infinity involved. Here, we're infinitely positive, and we're still infinitely positive, but we have this point of non-differentiability right here at 2. So our branches now, here is infinitely positive, getting more and more positive for the slope, the y values down here, and we're coming down from infinitely positive over here, and we're tapering out, so our slope numbers, our y values on the slope, are approaching 0. For this last one, we have a vertical asymptote, and the slopes on this one, we're going from infinitely negative to still infinitely negative. So this is going to be another vertical asymptote, but this one, both of the branches are going to be on the bottom, right? Infinitely negative, and then infinitely negative again. Now that we've got those building block kind of situations out of the way, we're going to deal with something a little bit more heavy duty, a few more things going on here. A good place to start when you're dealing with a bigger graph like this is to look for what I call critical values. This is actually the official name for anywhere where the derivative, f prime, is either 0 or undefined. You're going to see this word over and over, so it's a good one to learn now. I would start by finding and graphing these spots. So places where the derivative is 0, remember that's going to be smooth turnarounds. So we have, right here we have a smooth turnaround on the original. So the derivative, if we put it on the same graph, the same axis, will be 0 there. Here's another smooth turnaround, so that's a derivative of 0. Another smooth turnaround, derivative of 0. We also need to look out for places where the derivative is undefined, like cusps or vertical tangents or discontinuities. Those could give us asymptotes or holes in the graph, and we would want to graph those two right away. The more features like this you can put on the graph, the easier it's going to be to guide your graph when it's time to actually sketch the curve of your derivative. Now, the nice thing about critical values is that these are the only places where your derivative can change from positive to negative or vice versa. If you want to jump from one side of the x-axis to the other, you either need to go through the x-axis by crossing it, or you need to have something like an asymptote that lets you just kind of warp from one side to the other. In between these critical values, you're going to have to stay on the same side of the axis. So the next thing that would be good to do is figure out the sign of f prime on all of these intervals that you've just broken this up into with this critical value here. So for our first interval, we've got an increasing function, So that means we're going to have a positive derivative. And when we actually sketch our derivative, we're going to have to start up here. Next interval, we're decreasing, so that's negative. Next interval is increasing, so positive. And then we're decreasing for the last one. Don't assume it's going to flip-flop back and forth. You always have to double check. So now let's do one more thing. We're going to draw the curve. To do this, you just have to stay on the correct side of the x-axis, which you figured out what that is down here, and you have to touch all of these x-intercepts. Now in this case, we're going positive to negative to positive to negative. So we're going to go through all of those x-intercepts, but that doesn't always have to be what happens. But in any case, for this graph, here is the graph of f prime. So that last example is what I would call kind of on the milder end of these. Here's a hot example, if you will. So pause the video and try your best at this one. I would definitely recommend you try this in pencil. All right, let's see what we came up with. How did you do on those critical values? Let's look for undefined places first, because there's a few on this graph. So right here, as we come from the left, we see that we have this kind of jump hole sort of weirdness going on. But we also, down here, looks like we've got sort of a half of a cusp. So we have to be careful here. When you're deciding what to do for an undefined derivative, you have to choose between a hole and an asymptote for your derivative graph. Now, if your graph is approaching a constant value, like we appear to be doing up here, then you would put a hole there. So here, it looks like we're approaching 0, so a hole pretty close to 0 would make sense. But from the right side, you have an infinitely positive slope going on as you get closer and closer to -1. Whenever your slope is approaching infinity, you should have an asymptote. So we're actually going to do both. This is one of those weird places where you need a hole and an asymptote for different parts. For the left side, we need the hole. For the right side, we need the asymptote to guide us. Moving on, at 2, we've got this cusp going on. You can tell because it's kind of getting steeper and steeper as you get closer there. This graphing stuff is where we have to care if we have a corner or a cusp. With a corner, you're approaching different constants, so your derivative would jump. With a cusp like this, you're approaching different infinities, so you need an asymptote for your derivative graph. So we will have an asymptote for that. And notice now, looking for other critical values, we have a smooth turnaround right here. So that's going to be an x-intercept in that area. Let's go through now and find the derivative sign for every interval here. First interval, we've got a positive slope. We have increasing, so a positive slope for the next one as well. But then we change to negative after that smooth turnaround. And after our cusp, we're positive again on our slope. So putting it all together, we're starting positive. So we're going to start above the x-axis. And we've got to move toward this open dot here. Notice that your slope is getting smaller and smaller, so we're going to be gently coming in for a landing here. Now after that, we have an infinitely positive slope, so we're going to start up here. We have to come through this x-intercept, and this is an infinitely negative slope down here. So a graph that looks like this would make the most sense. After that, we have an infinitely positive slope right here, so we're back up here again, and this looks to be kind of tapering off towards a slope of 0 as we go, so something in that neighborhood would work. Now, on this example and the next one, having both graphs in the same place is kind of cluttered, I agree. So here was the original, and just for your own reference, here was the derivative graph that we got off of that. Now, I take that back about what I said about the next 2 examples. This is the last example. I mean, it's hot enough here, right? So till next time, Mr. Sutton signing off.